Okay. So, now principle of the induction motor, right. So, the operation of a 3-phase induction motor is based upon the application of Faraday's law and the Lorentz force on a conductor, right. So, suppose you have a this is your conductor having length L, right, and you have made a ladder and both sides the 2 bars are connected, right. So, in that case all the materials are conducting. Now, suppose a permanent magnet is placed on the top of this conductor. So, now if you now this is A, this is B, this is that at conductor length is L, and this actually flux density, this is the B flux density. Now, if you drag the conductor, right, drag this magnet to the right hand side with a speed V, say, then flux will cut. Therefore, what will happen? Because of that, a voltage E is equal to B in, this is the flux density B. So, a voltage E is equal to B into L into V will induce, right. So, in that case, what will happen? That because of that, a current will flow. This is the current I, and immediately that half of the current will flow through this, half of the current will flow through the your what you call conducting your through this conductor, right. So, in that case, as assuming that you are holding this ladder, you are not allowing it to move, but if you make it free, then what will happen? That that ladder also will move in the direction of the your what you call in the direction of the magnet. As magnet is moving, we are moving the magnet to the right hand side and keep a very little gap between this conductor and the magnet. So, in that case, that if ladder also moves there, so there will be a relative speed between that magnet and the ladder. So, finally, that voltage E also will reduce and the current also will reduce or diminish, right. So, from this concept only, the principle of induction machine has come, that how it rotates, because it is self starting. So, we will come to that, right. So, in this case, this diagram I have taken from a book, right. So, in this case, the 4 things will happen. A voltage E is equal to B L V is induced in each conductor while it is being cut by the flux. So, this is Faraday's law. Now, the induced voltage immediately produces a current I, which flows down the conductor through the end bars and back through the other conductors. I told you current I and I by 2 on both sides, right. And because the current carrying conductor lies in the magnetic field of the permanent magnet, it experiences a mechanical force that is called Lorentz force, and the force always acts in a direction to drag the conductor along with the magnetic field. Now, if the conducting ladder is free to move, now you are allowing to move, then it will accelerate toward the right. However, as it picks up speed, your conductors will cut less rapidly, because relative speed will go down, right, with the result that the induced voltage G and the current I will diminish. Consequently, the force acting on the conductor will also decrease, right. So, if the ladder were to move at the same speed as the magnetic field, the induced voltage G, the current I and the force would all be 0, because relative speed will be 0, right. So, therefore, in an induction motor, the ladder is enclosed upon itself to form a squirrel cage. If you just fold it, right, so it looks like a ladder will look like your what you call the squirrel cage, right, and the moving magnet is replaced by rotating field. So, there in this diagram for the purpose of explanation, we have taken a moving magnet, but in the what you call in the induction machine, it will be a 3-phase magnetic field, the rotating magnetic field, and if you enclose this ladder, it will look like your squirrel cage. That is why this example is this diagram is taken. So, in this case, your what you call that it looks like your in an induction motor, the ladder is enclosed upon itself to form a squirrel cage, and the moving magnet is replaced by a rotating magnetic field, right. So, the field actually is produced by the 3-phase current which flow in the stator windings. So, now this is a schematic diagram, this figure I have taken from a book, right. So, this your what you call this part, your external circle, this part actually this part external one, this is actually stator part, right. So, and that other part, this part which I am making it here, this is actually say your rotor part, right, and in between stator and rotor, the small gap is there. I told you this is that air gap, right, this small gap, this is the air gap, right. So, uniformly it is uniform. So, I told you depending on the rating of the machine, it may be 0.4 to 4 millimeter, right, or may vary also as per the rating of the machine. So, now this is your this and this A, B and C, this is actually 3 phases are there, A, B, C, 3 phases, right, 3 phases are there. So, it is schematical, it is shown. Similarly, inside the rotor also you can see something, this is actually direct T, TL you need not bother now, because we will see the basic thing only, and these are your what you call, these are your what you call the 3 phase terminals. The way we have seen 3 phase A, B, C, here also 3 phase terminals, same thing, and it is connected to a bus bar called infinite bus, where voltage and frequency is constant. So, what is infinite bus? Right now you need not bother, you assume it is connected to the 3 phase supply, where voltage and frequency will remain constant, right. So, now question is, and your what you call, and this speed n, actually this is the speed of the rotor, and n is that speed of the your what you call that your rotating field. Now, 3 phase single phase circuit, where we are studying, we are trying to find out some speed ns, right, that is considering pair of p poles, right. But in this case we will take that the formula is there, that synchronous speed is equal to 120 f by p, p is number of poles. For example, if f is equal to frequency is 50 hertz and p is equal to say 4 pole machine, that p is equal to 4, no question of pair, only poles. So, ns is equal to your 120 into 50 divided by 4, right. So, it will be 1500 rpm, right. So, if induction machine is of your what you call that your generally you will find it will be your p pole 4 pole machines. So, in that case its speed will be, later we will see, if it acts as a motor, its speed will be less than your 1500 rpm, right. And if it is if it runs as a generator, it will be just above 1500 rpm. We will not discuss about induction generator, only little bit about motor, right. And generally you will find it is a 4 pole machine, but the magnetic field, the 3 phase magnetic field, it's rotate at a synchronous speed ns, that is say 1500 rpm for example, and this n is there, this is the speed of the rotor, which will be less than the your synchronous speed ns, right. So, now whatever this thing it is here. So, what will happen? So, consider a cylindrical rotor machine with both the stator and rotor run for 3 phase as shown in figure, right. This upper part is a stator and inside circle is a rotor, and between that air gap is there. Now, assume initially the rotor winding to be open circuited and let the stator be connected to an infinite bus. That means, you assume the rotor is open circuited, it is not short circuited. First, for our understanding, you assume the rotor is open circuited, and stator it is connected to a supply where voltage and frequency both are constant, right. The stator current set up a rotating magnetic field in the air gap, right, which runs at synchronous speed, inducing EMF in the stator winding, which balances the terminal voltage under the assumption that the stator resistance and leakage reactance are negligible. Now, as soon as you supply your stator, when you are connecting the stator terminal to a voltage, your supply voltage, right. So, naturally that voltage will also induce in your what you call in the stator winding, and it creates a rotating magnetic field which rotate at a synchronous speed, your what you call ns, right. So, this is F1 is given actually stator MMF, or that F1, right. So, arbitrarily it is taken, right, but this magnetic field rotating at a synchronous speed ns. Actually, electrical engineering many things are not visible, right, like your magnetic field you can feel it, but you cannot visualize voltage current, you can see the waveform other things, but you can feel it, but you cannot see in your open eyes, only you can see that waveform, right. So, flux also it is not a visible quantity, only you can feel it, right. So, similarly here your what you call, only you can see their waveform, the pattern, but eyes you cannot see that how is it, right. So, in that case the stator current set up a rotating magnetic field in the air gap which runs at synchronous speed, inducing EMF in the stator winding, that is your F1 I showed you, which balances the terminal voltage under the assumption that the stator resistance and leakage reactances are negligible, right. Now, also that your rotating field induces EMF in the rotor winding, because rotor is also there. So, field is rotating. So, it will also induce your what you call EMF in the rotor winding, but no rotor current can flow, because we have assumed the rotor is open circuited, right. So, the frequency of the rotor EMFs of course f, because rotor is not rotating. So, frequency of the rotor EMF is also f, right. Since the rotor MMF f to 0, because rotor is open circuited. So, no current is flowing. So, rotor MMF at this stage f 2 is equal to 0. That means, this diagram that is arbitrary, it is made it that f 2 is equal to 0, right. So, in this case your the no torque developed and the rotor continues to be stationary. So, rotor is not moving, it is stationary. Now, the machine you acts merely as a transformer, where the stator we call say primary like transformer and the rotor the secondary have EMFs of the same frequency induced in them by the rotating magnetic flux rather than by a stationary time varying flux as in an ordinary transformer. Transformer we have seen that suppose phi is equal to phi max or sin omega t, right. So, but here it is a that was a stationary time varying flux as in ordinary transformer, but here it is a rotating your what you call magnetic flux, because you are giving 3 phase supply to the stator winding. Now, let the rotor be now held stationary, that is blocked from rotation. Now, rotor is not open circuit, it is short circuited, but you are not allow the rotor to rotate, say you imagine, and on the rotor winding be short circuited, right. In this case the rotor now carries 3 phase currents, creating the MMF f 2 rotating in the same direction and with the same speed as the stator field. Now, if here it is in the diagram this is my f 2, but we are not allowing the rotor to rotate. Here it is given ns minus n with respect to rotor or ns with respect to stator. So, when rotor is you are not allowing the rotor to rotate. So, it actually this f 2 actually this n is actually what will happen, that the speed of this MMF, right, it will be just ns with respect to stator, because you are not allowing the rotor to rotate, but as soon as you allow the rotor to rotate with n, it will be ns minus n, because relative speed with respect to rotor, right. So, in this case let the rotor be now held stationary and the rotor winding be short circuited. So, naturally if the current will flow, therefore, MMF will be there in the rotor, right. So, but with the same speed as the stator field, because rotor is we are not allowing the rotor to rotate. Now, f 2 causes like your transformer, f 2 causes reaction currents to flow into the stator from the bus bar bracket, whatever is written, just look into this, such that the flux per pole, that is phi r of the resultant flux density wave induces a stator EMF to just balance the terminal voltage. This is same as your philosophy is to some extent will be like transformer, right. So, f 2 causes reaction currents to flow into the stator from the bus bar, such that the flux per pole, that is a phi r of the resultant flux density wave induces a stator EMF to just balance the terminal voltage, because now current is flowing to the rotor. Now, obviously phi r must be the same as when the rotor was open circuited, right. Even when the machine is loaded also, this phi r will remain more or less constant, right. In fact, phi r will remain constant independent of the operating condition created by the load on the motor. Now, the interaction of phi r and f 2, that is the resultant flux phi r and f 2, which are stationary with respect to each other, right, creates the torque tending to move the rotor in the direction of f r. The induction motor is therefore a self starting device, right. So, this interaction between phi r and f 2, right, which are stationary with respect to each other, creates the torque and tending to move the rotor in the direction of f r. So, this is that your diagram, this is your that resultant flux phi r and f 2 will interact with each other, and this will be the your what you call the direction of this your direction will be your what you call this resultant will be f r, right. So, this way if you look into this this one, right. So, this phi r and 2 just with respect to each other creates the torque tending to move the rotor in the direction of f r. The induction motor is therefore a self starting device, right. So, let the short circuit rotor be now permitted to rotate. Now, you make it to freeze, so the rotor will rotate. Now, if it rotates, it runs in the direction of the stator field and acquires steady state speed of n, right. So, it will rotate in the direction of your what you call that your this in f r, right, with that ns, that same your synchronous speed, but now the rotor is rotating, that rotating in the direction of the your what you call same direction of the magnetic field. So, naturally what will happen, this as rotor is rotating with the speed n which is less than ns, right, which is less than ns. So, that means rotor will rotate in that your what you call in the same direction of the your what you call that your rotating magnetic field, but it will never catch ns. If it catches ns, then n minus the relative speed will become 0 then, right. So, in this case it runs in the direct stator field and acquires a steady speed of n, obviously n less than ns, because if n is equal to ns, the relative speed between the stator field and the rotor winding will be 0, right, and therefore, the induced EMF and rotor currents will be 0 and hence no torque is developed, right. Therefore, the rotor thus cannot reach the synchronous speed ns, it will slip actually, it will be for induction motor that n should be less than ns. With the rotor running at n, the relative speed of the stator field with respect to the rotor conductor is ns minus n, right, because both are moving in the same direction, in the direction of the ns. The frequency of induced EMF and current in the rotor is therefore, it will be ns minus n is equal to 120 f2 by p, that is your f2 is equal to actually this f2 is equal to actually it is rotor your frequency, and this is your ns minus n is your is the you have to call that the relative speed, and ns minus n 120 f2 upon p. Now, f2 is equal to can be written as, you write f2 is equal to p into ns minus n upon 20, the numerator and denominator you multiply by ns, numerator and denominator, right. And this part ns minus n upon ns, this part we define as your s, that is the we call slip, right, and your and this one, this part is f, because ns is equal to 120, I showed you earlier 120 f by p. Therefore, your p is equal, your what you call p is equal to your this thing 120 f by your ns, right. So, this one you can write is that this is your what you call ns into p upon 120. So, this is your this part is s and this part is your what you call the f is equal to p ns, rather than this one you write f is equal to p ns divided by 120 from this equation f is equal to. So, this is s into f, the rotor your frequency f2 is equal to s into f when rotor is moving with a slip s, and s is equal to your ns minus n upon s, right. So, it is called the slip of the rotor, right. The slip s is the per unit speed, this is dimensionless quantity with respect to synchronous speed at which the rotor slips behind the stator field, right. So, ns minus n is the difference of the speed divided by ns, it is a dimensionless quantity. So, that is why we call the slip s, right. The rotor frequency f2 is equal to sf is called the slip frequency, but when machine is stand still at that time s is equal to 1, because at that time n is equal to 0, when rotor is not moving n is equal to 0. So, at that time your what you call s will be 1 at standstill. So, from equation 2 easily you can write n is equal to 1 minus s into ns. So, this is equation 3. From equation 1 you can also write that 120 s into f upon p is because f2 is equal to sf, right. So, that is why 120 sf upon p is equal to ns minus n, this is equation 4, right. Since the rotor is running at a speed n and the rotor field at ns minus n, right, with respect to the rotor in the same direction, the net speed of the rotor field as seen from the stator is, it will be just n plus ns minus n is equal to ns. Look at that, since the rotor is running at a speed n, right, and the rotor field at ns minus n, right, with respect to the rotor in the same direction, that the net speed of the rotor field as seen from the stator is your ns. So, in this case again I am going back to this diagram, I am going back to this diagram. So, this is your ns minus n with respect to rotor, right, and if it is your what you call, if you add n, right. So, what it will be actually same as your speed of the rotor field, that is your ns, and this is the direction of the torque is given, we will see little bit of that, right. And that is from this schematic diagram I thought it will be better your what you call, it will be better understanding. And one thing is there, this f2 f this what you call this f1 f4 f2 all are your what you call stationary with respect to each other. This is also moving with ns, this is also moving with ns, right, and so all these things will be stationary because you are what you call, therefore, this and this is the angle delta between fr and f2 dash, right. So, all these things will remain stationary. So, here, so this is your what you call that with respect to the rotor, there is the same direction, the net speed of the rotor field as seen from the stator is, it will remain as your ns, right. So, that is same of the stator field, that is rotor field and stator field both are moving at the same speed ns. Thus, the reaction field F2 of the rotor is always stationary with respect to the stator field F1 or the resultant field Fr with respect with flux phi r per pole, right. So, that means your reaction field F2 you have drawn, right, in the diagram of the rotor is always stationary with respect to the stator field F1 or the resultant field Fr, right. So, all these things are remain stationary. So, now circuit diagram of a 3-phase slip ring induction motor with delta connected stator and Y star connected rotor is shown in this. This is the stator winding, this is the 3-phase supply, right, and this is the rotor winding, this AC to the voltage induced in the rotor we will see later, right, and this is your what you call that brushes are there, slip rings are there to be shorted through resistance at the time of starting. This will do it when you perhaps in your second or third year when you will do the induction motor experiment, right, 3-phase induction motor experiment, at that time you will see this on rotor motor. So, in this case the rotor or rotor winding is connected to slip rings which are shorted through your external resistance at the time of starting. The resistances are cut out as the motor attains full speed. Here it is resistance here are not shown here, it is not shown here, right. So, the rotor of a squirrel cage motor has permanently shorted bars there. So, this can be replaced from a your what you call circuit point of view by an equivalent wound rotor. In the case of squirrel cage motor, all these things are not there because rotor itself is shorted. So, from equation 2 we can write slip is equal to ns minus n upon ns. This is ns minus n called slip speed and this is your synchronous speed. Sometimes if it is a numerical, if it is a slip speed, then we will take the difference of these two ns minus n, right. It will be for motor, it will be always positive, right, and therefore, S is equal to 1 minus n upon ns. This is equation 5. Now, obviously, for n is equal to 0, that is when rotor is stationary, S is equal to 1, that is for the stationary rotor, and S is equal to 0 for n is equal to S, that is for the rotor running at synchronous speed, right. So, from equation 1, the frequency of the current induced the rotor is same as F2 is equal to SF. This we have seen, right. Frequency of induced your what you call your currents induced in the rotor is F2 is equal to SF. This we have seen. The normal full load slip of the induction motor is of the order of 2 to 8%. So, that the frequency of the rotor current is as low as 1 to 4 hertz, right. If it is 2% and slip is 2% and F is 50 hertz. So, it will be hardly your what you call F2 will be 1 hertz because 0.02 into your 50, right. So, per phase now next is the per phase your what you call stator EMF is given by U1 is equal to say pi root 2 like transformer kW1 n phase 1 F into phi r. So, kW1 is winding factor. I am not discussing this here, just you keep it in your mind because more you will study in your electrical engineering in your third year induction machine, and this is n phase 1, that is n pH1, that is the stator side actually number of turns we call n pH1, and F frequency and phi r is the flux per pole. So, per phase rotor EMF your what you call at S is equal to 1, the standstill rotor is given by when S is equal to 1, rotor is a standstill, at that time EMF will be pi root 2 kW2 n pH2 F phi r. The way you do in transformer, pi into root 2 multiply, it will become I think 4.44, right, and this is winding factor kW2 also called the winding factor of the rotor, and as if this is your primary side, as if this is your secondary side, right. So, E1 is equal to stator induced EMF per phase, E2 is equal to rotor induced EMF per phase, right. kW1 is stator winding factor, kW2 rotor winding factor, NPH1 stator turns per phase, NPH2 rotor turns per phase. The way you do transform this thing, and phi r resultant air gap flux per pole, right. Now, at any slip S, the rotor frequency being SF, right, therefore, the rotor induced EMF changes to AC2, because rotor frequency now changes to your F2 is equal to SF. therefore, the rotor induced EMF actually will be, it will be AC2, right. So, if it is sleep is 1, at that time it is E2, but when that when rotor is running, it has some sleep. So, it is induced EMF will be AC2. So, consider now the impedance of the rotor circuit for Z2 is equal to R2 plus JX2 when it is a standstill, right, when sleep is equal to 1. Now, when X2 is equal to leakage reactance of the rotor at standstill, that is rotor frequency is equal to stator frequency at that time, right. So, it is F. Now, when the rotor running at sleep S, at that time its frequency being SF, frequency is changing, therefore, its impedance changes to your what you call R2 plus JX2, right, because frequency is SF. Suppose when you make this one, when you make this one say general, say x is equal to L omega, right, omega is equal to 2 pi f. So, 2 pi f, your omega is equal to your 2 pi f, this L omega into you write L, right. So, but rotor frequency instead of f, it will become f2 and f2 will be sf, this one into L. So, it will be your what you call 2 pi f, the s is s into your what you call x, right, in general. So, this is your what you call your, that is why the rotor frequency will be now when rotor is running, its impedance will be R2 plus JSX2. R2 is resistant, but this reactance depends on the frequency. So, therefore, it is therefore seen that the frequency of rotor currents is induced EMF and reactance all vary in direct proportion to the sleep, because when rotor is rotating, its frequency is changing of induced EMF, current, as well as the reactance also, because this is F, right, because in general we know L omega, but in the case of rotor it will be F2 is the frequency, F2 is equal to SF. So, that is why S is here. Now, this is that figure 6 shows the rotor circuit as sleep S. This is the induced voltage rotor circuit. Rotor itself is a short circuit thing. So, this is R2 resistance, this is SX2. It is given as a your what you call that a variable symbol, right, and this is the current I2, right. So, in this case your this is the rotor circuit, because rotor is short circuited, so it is a closed path, right. Now, the phase angle of the circuit theta 2 is equal to tan inverse Sx2 upon R2, right. So, this is your theta 2, that is the lagging. Now, also E1 by E2, if you this expression if you make here, it is written that this expression you make it E1 by E2, you just divide E1 by E2, then it will be like this. E1 by E2 if you make, then it will be Kw1 NPH1 upon Kw2 NPH2, that is N1 upon N2 say, right. N1 is equal to Kw1 NPH1, N2 is equal to Kw2 NPH2, that is equal to say A, right. So, in this case where N1 N2 the effective stator and rotor transfer phase, right. So, that is your we are making like a transformer, we are making it. Now, development of circuit model next. So, circuit model is same as a transformer, say E1 upon E2 is equal to A. A is given N1 upon N2 and the current your I2 dash upon I2 is equal to 1 upon A, right. The way we did transformer same way, and E2 is equal to standstill rotor EMF, right. So, number 2, like in a transformer, the magnetizing current component Im of the stator current lags the stator induced EMF E1 by 90 degree, same as before. The number 3, the induction motor is not merely a transformer which changes voltage and current levels. It in fact behaves like a generalized transformer in which the frequency is also transformed in proportion to sleep, such that the rotor induced EMF is AC2 and the rotor reactance is SX2, right. So, these are the certain things. Now, when we derive that equivalent circuit like transformer, its coal loss component is neglected. This is stator side, as if your transformer primary side R1 X1 current is I1, this is I2 dash, right, this current is I2 dash, I1 is equal to Im plus I2 dash, and this is your voltage for an ideal, the way you make in ideal transformer, right, same thing. This is the voltage E1 and this side is frequency is given, mark is as F, right, and PM we will see it is a mechanical power output per phase, that is why divided by 3 we will see later, and this is figure 7a, and this is the rotor circuit, frequency is F2 is equal to SF and voltage induced of the rotor circuit, just we saw AC2, this is R2 SX2 and this is the current I2, right. So, next one is this is the first circuit, right. Next one is, and rotor is rotating with a speed of n, here it is n, right, here it is n, it is given like this. Now, Next one is this derivation is later. Next one is this side left hand side remain as it is. This is frequency f, this is frequency f2 is equal to sf. Now, this is rotor circuit, this is E1, this part will be SE2 is equal to SE1. Here it is ratio is A is to 1, here it is A is to 1, A is equal to your N1 by N2, A is equal to N1 by N2. So, here it is your ratio is given A is to 1, right. So, in this your what you call, now in this case it is 1 is to 1 and all this transform, all these things transform, this transformation is shown later. The way you do it transformer almost similar it will be there. R2 dash is equal to S square R2, Sx2 dash will be S into S square x2 and current here this side is I2 dash, right. Now, here if you look into this, I2 dash is equal to your, then I2 dash upon I2 is equal to 1 upon A, therefore, I2 dash will be equal to your I2 upon A, right. So, this side if you transform it will become 1 is to 1, it will become I2 dash is equal to I2 upon A and this SE2 will become SE1, this is 1 is to 1. Derivation, I mean without derivation also you just little bit if you can do it, you can easily do it this, but derivation is there later, right. Now, next is this right hand side you divide this thing by S, this all the parameters you divide by S, this side it is now 1 is to 1, this all the side you divide by S. So, after saying this I will come to derivation, at that time I will not come to this figure. So, what you do is that you divide all the thing by S, then if you divide everything by S then this will become E1, this will become your x2, your what you call x, this Sx2 dash divide by S it will be x2 dash and if you divide by this one it will be R2 dash by S. So, it will be x2 dash R2 dash by S and this is your what you call E1. So, here it is not shown again 1 is to 1, right. So, this is frequency f, this is frequency f now, right, because everything is made in terms of this side, right. So, now here it is also because everything divided by S. So, here it is now equivalent circuit, now it is f2 is equal to Sf, now it is frequency is f because this is E1, this is E1, this way you have made it. Now, this next what we will do, next as this is E1, this is E1 like transformer. So, these two things will come to this side, we will bring it, right. So, if you bring it, it is x2 dash and R2 dash and circuit is closed. So, this is your what you call induction machine equivalent circuit, but RC is not shown here, we will show it. So, this is the equivalent circuit of the induction machine, right. So, now if you add that coal loss component like transformer, then this branch has come, rest is same, but this branch has come. Now, how these things are coming? Now, this is the development of the equivalent circuit of induction motor, but how things are coming. The circuit model of the induction motor can now be drawn on per phase basis as shown in figure 7a. Now, all these things I have told you. So, all this write up is here, just go through it, right, just go through it, right. So, look at this derivation, I2 is equal to, you can write AC2 upon R2 plus JSX2 from that the rotor circuit diagram in that first one figure 7a. So, in that case you can make it your what you call numerator and denominator you multiply by A. So, SAE2 then AR2 plus JSA into X2, your numerator and denominator multiply by A. We know I2 by A is equal to I2 dash, therefore, this I2 denominator you multiply by A again. So, it is I2 by A is equal to I2 dash. So, SAE2 S square R2 plus JS S square X2. So, this part can be written as that your E2 can be your what you call this E2 can your AE2 can be written as E1 because E1 by E2 is equal to A. So, it is AC1 divided by S square R2 plus JS S square X2, right. Therefore, define Z2 dash is equal to S square R2 plus JS S square X2, that is R2 dash plus JS X2 dash. R2 dash is equal to this much, X2 dash is equal to this much, right. So, that is why whatever we have made it here, I am going to this circuit, whatever we made it here AC2, then it is ultimately it is AC1, easily you can make it, right. So, that is why this AC1 is here. So, similarly, here it is we have derived it from that your what you call from this one, this is actually AC1. So, this is the equivalent parameter of the induction machine, same as the transformer, numerical also will do to some extent this thing, right. Or I2 dash you can write AC1 upon this thing. So, divide numerator and denominator by S, therefore, it is coming I2 dash is equal to E1 divided by R2 dash plus JX2 dash, that is everything is transformed to the stator side, right. So, the simple tricks refer to the rotor circuit to the this simple trick refers to the rotor circuit to the stator frequency, because at that time your what you call right hand, this circuit is referred to your like your stator frequency, because this circuit here it is now frequency f, here also frequency f, here it was sf, here it is sf, but this one has divided by s. So, it is this side frequency is f, this is a frequency, this is a simple trick, right. So, this is your what you call that I2 dash. So, this simple trick refers to the rotor circuit to the stator frequency. Now, if R2 dash is separated from R2 dash by S to represent the rotor copper loss as a your separate entity, the circuit model is shown in figure 8a, right, in which the variable resistance represent the mechanical output in electrical form. That means, your what you call that means this your resistance is, that is your we got R2 dash by S, this is the thing, right, but stator side your what you call a resistance basically R2 dash. Therefore, what you do, you subtract R2 dash then add R2 dash, right. That means, this one can be written as R2 dash plus you take R2 dash common, it will be 1 upon S minus 1, right. So, this again I have taken from a book. So, this one if you look into that, I make it here because I represent everything by small letter. So, basically R2 dash is nothing but small r2 dash, x2 dash is nothing but a small x2 dash, r1 is nothing but a small r1, capital X1 nothing but a small r1, and capital Xm is nothing but a small xm, and this is Ri, right, and this is the current I0. Similarly, your Ri is nothing but a small Ri. So, and this is separated, right, this rotor circuit, this part is separated, this is actually rotor your reactance and this is your resistance, and rest this is whatever this part, right, this is actually mechanical power output, because R2 by S, S is variable, right. So, it is slip. So, just take it out, take out this one, rest will be R2 dash into 1 upon S minus, this is the mechanical power output, that is called gross one, right, we will see that. So, that means, this is this circuit actually this circuit is R2 dash upon S. Once again I am telling you, this R2 dash by S can be made two things. One is you add R2 dash plus you can write, you take R2 dash common, then 1 upon S minus 1, then add R2 dash, subtract R2 dash. So, this part is coming there, what was circuit I shown it. So, this part actually separated, the rotor resistance is separated, right. So, that is why this circuit is like this, is actually mechanical output, right. So, many meanings are there, but this is say figure 8a. So, nothing, this is basically if you add these two, it will be R2 dash by S, right. So, so alternatively the circuit model of this thing could be used like this. I mean, if you neglect that this component, this Ri component, so it can be you use like this, your what you call R2 dash, X2 dash, R2 dash, here it is actually just hold on, here it is, there is a this R2 dash actually printing mistake is here, here R2 dash should be there here, right, a printing mistake is there in the diagram. So, it is R2 dash and this is your coal loss to be subtracted. I mean, here all coal loss whatever was there, so that branch is removed, but for this part this R2 dash 1 upon S, here coal loss also has to be subtracted if you remove this, a simplification, right. So, this is another thing is that the corresponding wherein the iron loss resistance Ri omitted, and this loss would be subtracted from the gross mechanical output, that is power absorbed by R2 dash 1 upon S minus 1, this one, right. Now, this amounts to certain approximation which is quite acceptable in the normal range of slip in an induction machine, this is an approximation. It may be noted that the power dissipated into R2 dash into 1 upon S minus 1 includes the coal loss, that is figure 8b, which must be subtracted from it to obtain the gross mechanical power. When you will do the numericals, few numericals I will show you. For getting net mechanical power output, the windage and friction loss must be further subtracted from it. Windage and friction loss, right, frictional loss, sometimes we call it a rotational loss, that will be given some percentage of this, right. The coal loss, windage and friction loss together are lumped as rotational loss, as both these losses occur when the motor is running, right. So, the rotational loss in an induction motor is substantially constant, right, at constant applied voltage, and motor speed varies very little from no load to full load, not much change in the no load to full load. Only thing is that for numerical solving, net mechanical power is equal to shaft power. This thing you have to keep it in your mind. Shaft power means net mechanical power, right. So, another thing is the approximate circuit model. Approximate circuit model is shown like this. That means, all these things, this branch put here only, and others are clubbed together, but this kind of analysis will give you erroneous result, because like a transformer, this I0 actually very small, right, but in induction motor it will be maybe 30 to 50% this I0. So, this kind of calculation if you do for simple using the simple circuit, result will not be accurate, because this I0 will be very high for induction machine, it will be 30 to 50%, right. So, this approximation, everything what I said, it is written here, right, everything is written here. So, further the primary leakage reactance is also necessarily higher, what you call higher in an induction motor compared to a transformer, and so ignoring the voltage drop in primary reactance is not quite justified, right. So, induction machine, you have to when you solve the numerical, you have to consider your what you call that your accurate model, right. So, therefore, the result obtained by this model are considerably less accurate, right, and this I told you. Magnetizing shunt branch which draws current I0 at almost 90° lagging, the power factor at which the motor operates at full load is low, about 0.8. At light load, that is small I2 dash, the machine power factor is much lower. This is the inherent problem of the induction motor, because of the presence of the air gap in the magnetic circuit, right, and the fact that the excitation current must be drawn from the mains, that is the stator side, right. With this, thank you very much, we will be back again.